Hey guys, welcome back. Mr. Marone here. So we are into chapter 7 now, which is all about similarity and more in particular triangle similarity. We're going to start off by talking about a thing very similar to transformations, but it's a non-isometric transformation. So we talked about those transformations, the translation, the rotation, and the reflection like crazy back in the fall. And we had one more to do, but it was non-isometric. The shapes are going to change a little bit, and we're going to dig into that more, and that's where dilations comes into play. So a dilation is a stretch or a shrink of a given figure. The best way I can think of it when you're dilating a figure is when you are enlarging or reducing the size of a picture when you place it into PowerPoint or you place it onto a Google Doc. So the big key to this is that a dilation is a stretch or a shrink where the angles remain the same. The angles are going to stay congruent, but the sides are going to be proportionally larger or smaller. So picture if you have an image and you grab the middle box. You know how the picture has, I should probably change from that. You know how a picture will have little boxes here, 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 and here. If you were to grab that box or this box, it wouldn't keep everything the same. It would stretch it out. It would look really wonky. But if you grab this box here, it makes the whole thing proportionally bigger or smaller. That's really what we're doing when we dilate a figure. There's two methods for doing this on a coordinate plane. The first way is the ratio method. We're going to use this idea of a scale factor. You're going to see this word scale factor a lot. Oops. You're going to see that word a lot, and that's the factor that we're going to multiply by to make a figure bigger or smaller. And you're going to use that to stretch a figure further away from a center or further towards it, depending on what the value of the scale factor is. And that's that center of dilation. So in this picture, the factor was a half. So we were getting smaller. We were making this figure smaller by a factor of a half. So as we do that, you're taking the distance from this center of dilation to your original point. Let's just pick a number and say that that was 8 units away. Well, half of 8 is going to be 4 units. And so I'm going to make my new one go 4 units away. I'm going to go half the distance between that point on the same line. So you can actually draw a line from the center of dilation through your original pre-image point and your image point with this. So that's the ratio method. The parallel method is to draw in your lines, draw in your rays that go through each of those, and then use parallel lines to figure it out. It's a much more difficult method to use. Before we go into a couple examples of using dilations and messing around with them, this is the full definition of a dilation. I'm going to let you read it, and there's a lot of math jargon in here, so I'm going to translate a little bit. But the first thing is, right here, that's how we denote a dilation. So just like how we use a capital R for a reflection, capital T for translation, this is the units right there. So the first thing you're going to have is the big capital letter D for dilation. And then the two pieces of information in the parentheses, the first one is the scale factor, and then the second one is the center of dilation. C is the center of dilation. A couple things to point out. When we have a scale factor larger than 1, this is known as an enlargement. The figure is getting bigger. When we have a scale factor less than 1, or I'm sorry, between 0 and 1, when it's a fraction, that is a reduction. If it's a negative, that's going to be something completely different. Okay? And like we said, every angle remains congruent to its image under the dilation. So the angles don't change. If we look closely at this picture, our original pre-image and our image in this segment are parallel. That will remain the same. Each of your new line segments will be parallel to their old one as well. So there's a lot of information there. You can read through it at your own pace. We're going to take a look at some examples now. So in this first one, they've given us rectangle ABCD. And then they've given us rectangle A prime, B prime, C prime, D prime in red. And the center of dilation is at point P. They want to know how are the side lengths and angle measures related. Well, we know from a dilation that the angles are going to be congruent, and we know that the sides are going to be proportional. So what we're going to do here is look at the scale factor. So if I were to look at the distance from point A and point P, that's a distance of 2 units. And then I take the distance from P all the way out to A prime, that's a distance of 1, 2, 3, 4, 5, 6 units. If I want to figure out what my scale factor is, all I have to do is take a single distance between image, so from P to A prime was a value of 6. From P to A was a value of 2. If I divide those, that's going to give me my scale factor. So in this case, 3 is my scale factor. So if we're considering what's the difference between A, B, C, D, and A prime, B prime, C prime, D prime, this one is 3 times larger because the scale factor was 3. We're going to use the same process here for number 2. So in this case, they gave us our original figure in black, our new figure in red. You can look at it and see it's gotten bigger. The little primes are telling us this is my image, and you can tell it's gotten bigger. So if we get a scale factor not bigger than 1, we've done something wrong. So if you look closely, LK had a measure of 12. L prime K prime had a measure of 10. So I'm going to take my image measure 18 over my pre-image measure 12, and then I'm going to simplify that fraction. I can pull a 6 out of each of those, and I get 3 over 2. So that is my scale factor. So it went up by a value of 3/2 or 1.5, 1.5 times bigger. All right. Our last one is going to actually ask you to graph this. So they want to know what are the vertices of a dilation by 1/4 of triangle PQR. Notice that they didn't give you a center of dilation. If they do not provide a center of dilation, it's the origin. So it's going to be the point 0, 0. So what you're going to do for each one of these is you're going to find the distance from the origin to point R. And then we're going to cut it into fourths. So point R is the point -4, 0. So the distance between those 2 points is a distance of 4 units. So if I were to take and make 1/4 times 4 units, it's going to give me 1 unit. So that means my new point is going to be right there. That's R prime. Okay? I'm going to use the same method to get points P and Q. So looking at point Q is the point 11, -4. 12, -4. Well, if we're cutting each of those by 4, Q prime, if I do 12 times 1/4, I'm going to get 3. And if I do -4 times 1/4, I'm going to get -1. So the point 3, -1 right there is Q prime. The distance from the origin to Q prime is going to be 1/4 the distance of original point Q. And our last one is point P. Point P is the point 8, 4. Well, if I do 8 times 1/4, I get 2. If I do 4 times 1/4, I get 1. So P prime is the point 2, 1. So if I connect those, I now have a dilation 1/4 the size around the origin. These things take time to practice, so you don't get frustrated if things get difficult. They take a little bit of time to get used to. If you have any questions, bring them into class tomorrow, and I look forward to seeing you then. Bye.